Finding real zeros of a polynomial function. A real polynomial function is of the form f of x equals ax to the n plus bx to the n minus 1 plus dx plus e with real number coefficients and whole number exponents. A real number c is called a real zero of f if f of c equals 0, if we can plug c into the function and get out 0. The real zeros of f of x represent x-intercepts on the graph of the polynomial. Some polynomial equations can be solved by advanced factoring techniques, but others require a longer process involving finding possible rational zeros and using a form of long or synthetic division of polynomials, and that's what we're going to learn next. Before we get into the main part of what we're going to be learning, I want to do a brief review of division just to remind ourselves of some terminology and think about things in a slightly different way. So if we have something as basic as 25 divided by 3, a lot of us can do this in our head. We could think, okay, how many times does 3 go into 25? Well, it goes in 8 times with a remainder of 1. And so we'd see this written as 8 1/3. But I want to think about this in a different way. I want to think about it sort of old school and thinking about taking 3 and writing it on the outside here as the divisor into the dividend 25. So if you remember, these have terms associated with them. The divisor goes into the dividend. And the way that we thought about it was, okay, how many times does 3 go into 2? Well, it doesn't. So we move on and we say, how many times does 3 go into 25? I want to frame it in a slightly different way. Instead of thinking about it as go into, I want to think about it as, well, 3 times what integer gets me to 2? So there is no integer I can multiply by, or whole number even, to multiply 3 by to get to 2. So that's why I'd move on and think about, okay, 3 times what number gets me to 25? Well, there's a number that gets me close to 25 without going over, and that number is 8. And that becomes the quotient. So we have the divisor, the dividend. This number 8 is the quotient, and then we would multiply 3 times 8. That gives us 24. And we're going to subtract 24 from 25 because we want to know the difference. How far away am I still from going into 25 perfectly? Well, I'm 1 away, and so we call that number the remainder. In real old school, we might have seen this written as like R1, right? 8 with a remainder of 1. So I just wanted to kind of briefly review the terms here. And what I also want to do is sort of rewrite this information in a different way. In performing this division, here's what we can say about the number 25. We can say that the number 25 is equal to the product of 3 times 8. But it's not a perfect product, as in there is a number left over. So 3 times 8 plus 1. So I can rewrite the number 25 as 3 times 8, but plus 1. So there's a little follow-up question I have here. From this work above, can we say that 3 is a factor of 25? And the answer is no, 3 is not a factor of 25. And the reason is because the remainder here isn't 0. So in order to be a factor of a number, we want it to be one of the two numbers that we multiply to get to the original number. But if there's this extra number that I have to add onto it, if I have a remainder other than 0, then no, we do not have a factor of the original number. Now let's extend this thinking to dividing polynomials. So let f of x and g of x be polynomials. Then, when we divide f of x divided by g of x, the answer is going to be q of x plus the remainder r of x over the divisor g of x. Or another way we can think about this is that the dividend f of x can be rewritten as g of x times q of x, so the divisor times the quotient, plus the remainder. So if you think about what we just did with numbers right now, all of this should feel kind of familiar with the quantities that we were just working with when they're in terms of numbers. So we say still with polynomials, f of x is the dividend, g of x is the divisor, q of x is the quotient polynomial, and r of x is the remainder polynomial. Now let's look at the remainder and factor theorem. The remainder theorem says, let f of x be a polynomial function. If f is divided by the linear polynomial x minus c, then the remainder is simply f of c. So in other words, if we take a polynomial, divide it by a linear polynomial that looks like x minus c, to find the remainder, we can just plug in the value of c into f of x, and there we have it. Now we can also find the remainder by performing long division or synthetic division, which may or may not take more time than simply substituting in the value of c. Now the factor theorem. Let f of x be a polynomial function. If f of c equals 0, then x minus c is a factor of f of x. And if x minus c is a factor of f of x, then f of c equals 0. This is what we call an if and only if statement in mathematics. It works both directions. So if the remainder is 0, which is what this quantity represents, f of c equals 0 means the remainder is 0, then x minus c is a factor. And if x minus c is a factor, then the remainder must have been 0. Now, quick note, if our linear factor looked like ax minus b, then the 0 value would be b over a. So if we think about setting this equal to 0, I would add the b and divide the a to the other side. So f of b over a equals 0. And vice versa, this would also be an if and only if statement. If f of b over a is equal to 0, then ax minus b is a factor of the polynomial. In this example, we're going to use the remainder theorem to find the remainder when f of x is divided by x minus c. Then use the factor theorem to determine if x minus c is a factor of f of x. In this example, we're going to use the remainder theorem to find the remainder when f of x is divided by x minus c. Then use the factor theorem to determine if x minus c is a factor of f of x. In part A, f of x is x cubed plus 2x squared minus 5, and it's being divided by x plus 2. So here, the value of c is the value that makes this linear factor equal 0. So here, one way we could think about it is if I set x plus 2 equal to 0, I would subtract the 2 to the other side. So the value of c that I'm going to be working with, right, c is going to be negative 2. Or I could think about writing this as x minus negative 2 to see the value of c. Once I know the value of c, the remainder theorem says I can simply plug that number into the function and get my remainder out. So f of negative 2 is equal to negative 2 cubed plus 2 times negative 2 squared minus 5. So here we're going to get negative 8 plus 8 minus 5. So negative 2 squared is 4, 4 times 2 is 8. Negative 8 plus 8 is 0, so we end up with negative 5. So the remainder, when my function f of x is divided by x plus 2, is negative 5. Now the second part of the problem asks us to then use the factor theorem to determine if our x plus 2 is a factor of f of x. Well, this is really just a quick check of, is that remainder that we just found 0? No? Then no. X plus 2 is not a factor. So no, x plus 2 is not a factor of f of x because the remainder isn't 0. Right? The remainder isn't 0 because f of negative 2 was equal to negative 5. Now in part B, our function is 2x cubed minus x squared plus 2x minus 3, and it's being divided by x minus 1. So here the value of c is simply 1. So again, c is the number that makes this linear factor equal 0. So if I set it equal to 0, add the 1 to the other side, I get c equals 1. So that's the number I'm plugging into the function to find my remainder by the remainder theorem. So we're just going to have 2 times 1 cubed, so just 2, here minus 1 squared, so minus 1, plus 2 times 1, which is 2, minus 3. So here we're going to have 2 minus 1, so 1 plus 2 minus 3, which is 3 minus 3, which is 0. So by the remainder theorem, the remainder is 0 when x minus 1 is divided into this function. And because the remainder is 0, the factor theorem tells us that x minus 1 is a factor. So this time, yes, x minus 1 is a factor of f of x, because f of 1, the remainder, is equal to 0. So in other words, just to really clarify what we mean, we know that the function 2x cubed minus x squared plus 2x minus 3 will factor to x minus 1 times some other polynomial. Well, this is a first degree polynomial right here, right? X to the first. So times, and then some degree 2 polynomial would be left over, because that's the only way I'm going to get 2x cubed. So in fact, it's going to have to be something like 2x squared plus some stuff, right? With no remainder. That's the whole point, like plus 0, because we just found that the remainder was 0. So we don't know the remaining polynomial yet, but that's what's coming up pretty soon. Now in this example, we're going to verify that you have been given a factor of f of x, then factor the polynomial into linear and irreducible quadratics using synthetic or long division. Finally, find all the real zeros of f of x. So in part A, we have this polynomial function f of x, and we're going to first verify this truly is a factor of f of x. Now, to do that, we can use the remainder theorem. We can identify the value of c. So the value of c is -1 here. And we can substitute it into f of x to get my remainder and make sure that it's 0. So when the value of c is just -1, we just want to make sure that the signs are correct when substituting in. So here, this is going to end up being a -3, because a negative to an odd power stays negative. This is going to be +11, -5, -3. So here we just want to make sure, okay, this is going to give us +8 minus 5 is 3, 3 minus 3 is 0. So this is just really a check, right? It's like a verify that it does work out. Then factor the polynomial into linear and irreducible quadratics using synthetic or long division. So I'm a good candidate for using synthetic division when I am dividing by a linear factor. So here I'm going to go ahead and set up my synthetic division. So I'm going to go ahead and create my synthetic division setup with the 0 value. So -1 is one of the zeros. So I'm going to set that up on the outside, and then I'm going to go ahead and take all the coefficients of my polynomial, making sure that I'm going in descending power order, and I don't want to skip any power of x. So that's not a problem on this one, because I have every power of x represented, x cubed, x squared, x to the first, and then no x's at all. So I'm going to make sure and take the coefficient from each one of those. So I have 3, 11, 5, -3. And the way synthetic division works is we're going to go ahead and bring down the first coefficient 3, and then we multiply. So -1 times 3 is -3, and then we add down. So when we add down here, we're going to get +8, and then we're going to multiply again. So -1 times 8 is -8, and that number goes below the next coefficient. We add down, we get -3, and then finally we multiply again. -1 times -3, that's +3, and so we end up getting out 0. Now we're getting out 0 because we know that x plus 1 is a factor. We already found that the remainder is 0. When performing synthetic division, the number that's left over at the very end here, that's the remainder. So we already knew that it was going to be 0. Now these other values that come out, these are the coefficients of the quotient polynomial. These are the coefficients of the quotient polynomial. So let's go ahead and talk about what we have so far. So here's what we know so far, that the function f of x, 3x cubed plus 11x squared plus 5x minus 3, we know that that is going to factor to x plus 1 for sure. That's one of the factors. And then we need the remaining factors. Well, these coefficients here are the coefficients of the quotient polynomial. And the quotient polynomial is going to have to be of degree 1 less than the starting polynomial. Because if this is x to the first, I'd have to multiply something that's an x squared to get me to x cubed. So in other words, these three values, 3, 8, and a negative 3, are going to become the quadratic 3x squared plus 8x minus 3. So that's what I'm going to do, is come on over here, 3x squared plus 8x minus 3. So far I have a linear factor and I have a quadratic. But the question is, do I have what's called an irreducible quadratic? Or basically, can this be factored further? If it can, then we do have to factor it further. Now it does factor to 3x minus 1 times x plus 3. And then we bring down the factor of x plus 1. So here we now have all linear factors. So the original polynomial is now completely factored. Now the last part is, finally, find all real zeros of f of x. Well, we have one zero of f of x. We have negative 1. So from solving this first factor, when does this first factor equal 0? So I have x equals negative 1, and then I'm going to go ahead and look at the other factors. So 3x minus 1, I would add the 1 and divide by 3, so I have x equals 1/3. And then here, I'm just going to subtract the 3, so I get x equals negative 3. So all of my zeros are going to be negative 3, negative 1, and 1/3. So here are our answers. I'm going to go ahead and box them in. That's the factored version of the polynomial, and this is my list of real zeros. In part B, we have another polynomial function, and here's my linear factor, 2x minus 1. So here we want to be careful about, well, what is that 0? What is the value that makes this linear function equal 0? So here the c value is positive 1/2. So it's not just positive 1, that's the most common mistake here, just like taking the opposite of this number, but it's really about setting this equal to 0, so adding the 1 and dividing by 2. So what we can do is we can use the remainder theorem to verify we have a factor of f of x. We can plug in 1/2 into this polynomial. But we don't have to use the remainder theorem. It just says verify that we've given a factor. We can use the remainder theorem, or we can use synthetic or long division. Now, since we're going to have to factor this thing completely anyways, using synthetic or long division, let's just do that as a way of doing both at one time, verifying the remainder is 0 and setting myself up for those other factors. So let's start by setting up our synthetic division, because again, this is a linear factor. So we're going to put that 1/2 on the outside. We're going to take our coefficients, 6, 11, negative 19, and positive 6. And we're going to go ahead and perform our synthetic division. We'll bring down the 6. 1/2 times 6 is 3. Then we add down, so 11 plus 3 is 14. 1/2 times 14 is 7. So if I add down, negative 19 plus 7 is negative 12. 1/2 times negative 12 is negative 6. Negative 6 minus 6 is 0, right? So my remainder is 0. I have verified that I've been truly given a factor here. And notice that was a lot easier, I would definitely say, than trying to plug 1/2 in and cube it and 1/2 and square it and add all these together. So personally, I think that the remainder theorem is really only beneficial for plugging in like 1 and -1, maybe the whole number like 2. But past that, since we usually have to do synthetic division anyways, it's easier to test using synthetic division to find the remainder. So now, these values become the coefficients of a quadratic, because this was a cubic. So degree 1 less than that is going to end up being quadratic. So I have 6x squared plus 14x minus 12 as my remaining quadratic. So we know that the function, this time I'm just going to put f of x, right? So this whole entire function is equal to, so this time I'm going to write the quadratic part first. So I'm going to put 6x squared plus 14x minus 12. And then the linear factor, I'm going to go ahead and put x minus 1/2. So we said the value of c was 1/2, so we have x minus c as one of the factors. And you might be thinking, why didn't I put 2x minus 1? And you'll see why in just a second. So here, we want to see if we can factor this quadratic further. And first things first, we can take a 2 out of everything to make it easier to factor. So if I take out a 2, I have 3x squared plus 7x minus 6 times x minus 1/2. And now we're looking at whether this factors, and it turns out it does. So I have a 2 on the outside. It's going to factor to 3x minus 2 times x plus 3. And then we have that x minus 1/2. And we wouldn't typically leave something that looks like x minus a fraction as one of our factors. We typically want all integer values here. And that's where this 2 in the front comes in, right? So this 2, I can think about it as multiplying it times x minus 1/2, and then let's see what that factor is going to look like. So we'd have 3x minus 2, x plus 3, and then 2x minus 1. So again, I'm thinking about multiplying the 2 times this last factor over here, right? So just to be careful, this 2 doesn't distribute to all of the terms because this isn't addition or subtraction. That's when I would distribute. Here I'm simply using the commutative property, and I'm saying I can take this 2 and multiply it times this factor over here and arrive at my 2x minus 1 original given factor. And so now we can see, if we did multiply all of this out, the leading coefficient would be 6, and then the variable would be x cubed, because we have 3x, x, and 2x. So there'd be a 6 and then 3 copies of x, so there's my 6x cubed. So this is the factored version of f of x, and then my zeros are going to be 1/2, 2/3, and -3. So 1/2, and then if I set this factor equal to 0, I would add the 2 divided by 3, and here subtract the 3 to the other side. So really quick, we just want to be careful and not put 2x minus 1 right here and then leave this 6x squared plus 14x minus 12, because then 2x minus 1 times 6x squared will give us 12x cubed, and our leading coefficient, our leading term, isn't 12x cubed. So we have to realize that we identified the value of c 1/2 and use that to obtain this lower degree polynomial factor. So we had to use x minus c in our factorization at first, but then we could see how we end up getting back to that original given factor 2x minus 1. In this last example, we have our function and our factor x minus 2. Our value of c would then be positive 2 if I think about what makes this equal 0. We'll set up our synthetic division. Although it's not that hard to plug 2 into this particular polynomial, since we have to do synthetic anyways to factor it, might as well just jump straight to it to verify the remainder 0. So in setting up my synthetic division this time, I have to be careful because there's a missing variable term here. So I have 2x cubed minus 3x squared, but there's no just x term. And I do have to account for that when I write my coefficients in my list here. So I do want to put 2, -3, a 0 for what's technically in front of 0x, and then -4. So I want to account for any missing variables, to missing powers here. And I do want to make sure that they are in descending power order. So now we're going to perform our synthetic division. Bring down the 2. We have 2 times 2 is 4. We add down, we get 1. Now 2 times 1 is 2. If I add down, I get 2. And then 2 times 2 is 4. If I add down, I get that 0. Right? So I've verified I have been given a factor. And then 2, 1, and 2 are coefficients of my quadratic. So 2x squared plus x plus 2. So my function factors to x minus 2, the linear factor, times the quadratic 2x squared plus x plus 2. Now the question is, does this factor further? So 2x squared plus x plus 2. Well, it turns out it doesn't. So here, there's not two numbers that multiply to give us 4 and add together to give us that middle term of 1. So this is what we call an irreducible quadratic. It cannot be factored. So this is how we're going to leave our factorization. And then it says, finally, find all real zeros of f of x. So one of the zeros is positive 2. But then the question is, does this yield any real zeros? Now, just because something can't be factored doesn't mean it can't be solved, right? Because essentially what we're doing is we're asking, where does 2x squared plus x plus 2 equal 0? We're also asking, where does x minus 2 equal 0? But we do that in our head by simply adding the 2 to the other side. So if it's not linear, if it's quadratic and it doesn't factor, then what we can always do, of course, is use the quadratic formula. So we have x equals negative b plus or minus the square root of b squared, negative 1 squared, minus 4 times 2 minus 4ac, all over 2a, 2 times 2. Now, let's see, underneath the radical here, I have what's called the discriminant, and that's going to give me 1 minus 16. Well, 1 minus 16 is a negative number, so it's negative 1 plus or minus the square root of negative 15 over 4. Now, negative underneath the square root gives us an imaginary number. It doesn't give us a real number. So there are no other real zeros here, right? So my note that I'm going to put right here is that this is non-real, right? The second I have a negative underneath the square root. So that means the only real zero I have is 2. Now in the previous example, we were given a function and we were given a factor that we already knew worked. We had to verify that it worked, but we knew, hey, this factor works. So we had a starting place. But in general, we're not going to be given a starting place. We're just going to be given some polynomial and told to factor it and find its zero. So where do I even start finding a zero? Well, this theorem here is going to help us with that. The rational zeros theorem. This says, let f of x be any polynomial function of degree 1 or higher of the form f of x equals qx to the n plus ... plus p. So all this is saying here is that we're naming our leading coefficient q and our constant term p. Now, any rational zero of f of x must be from the possible factors of p divided by the factors of q. So I want to emphasize that only rational zeros are going to come from this list. So when we think about a polynomial, we could potentially have irrational zeros. Something like the square root of 2 can be a zero of a polynomial. But this list isn't going to give us that as a possibility. So as the name states, it's only going to give us possible rational zeros if we find the factors of p, the constant term, divided by the factors of q, the leading coefficient. So factors of last over first is what sometimes people say. All right, so let's see how this works. So in this example, list all the possible rational zeros of 2x to the fourth minus 5x cubed minus 11x squared plus 20x plus 12. All right, we only need to concern ourselves with the leading coefficient and the constant term. So we're going to go ahead and create a list. That list is going to be all the factors of 12, the last term, over all the factors of 2, the leading coefficient. So here, I look at the number 12 and I think about, okay, what are all the numbers that divide evenly into 12? So first we have 1, and then we have 2, and we have 3, and we have 4, and we have 6, and we have 12. All of those evenly divide into 12 with no remainder. But not only do we have those as a positive version, we can also divide by the negative of these. So I left a little gap because technically we have plus or minus 1 divides into 12, plus or minus 2, plus or minus 3, and so on. So we have to take all of those possibilities and divide them by the factors of 2. Well, the only factors of 2 are 1 and 2, but we have to include the positive and negative versions of those as well. So now what we're going to do is think about all the different possible combinations of these. So we have 1 divided by 1 and 1 divided by 2. So the final list here of the possible rational zeros is going to be every single possible combination. So what's 1 divided by 1? That's 1. So plus or minus 1. 1 divided by 2, that's 1/2. So plus or minus 1/2. And then we move on to 2. So we think about 2 divided by 1 and 2 divided by 2. So 2 divided by 1 is 2. But 2 divided by 2 is 1, and we already have 1 on the list, so we don't want to put duplicates. And then we're going to go ahead and move on to 3. 3 divided by 1 and 3 divided by 2. Well, 3 divided by 1 is just 3. 3 divided by 2 isn't on this list yet, so we'll leave that. Then we have 4. So we have 4 divided by 1 and 4 divided by 2. So 4 is not on the list yet, so we'll put plus or minus 4, but 4 divided by 2 is on the list because 2 is already here. And then we have 6 divided by 1, 6 divided by 2, 6 divided by 1 is 6, 6 divided by 2 is 3, that's already on the list. And then finally we have 12, 12 divided by 1, 12 divided by 2, so the only new one there on the list is going to be 12. So move that over a little bit, plus or minus 12. So you have to think about all of those combinations, all of the factors of 12 divided by all the factors of 2, and all the ways we can break these down. So this over here is my list. These are all of my possible rational zeros. So how many numbers are here? So we have 1, 2, 3, 4, 5, 6, 7, 8, but there's plus or minus of all of them, so there's 16 possible rational zeros. And sometimes you might see the abbreviation PRZ. So there's 16 possible rational zeros for this particular polynomial. Now in this example, we want to use the rational zeros theorem to find a real zero of the polynomial. So we have the same polynomial as before that we just worked with. Then we want to use that zero to factor the polynomial over the real numbers into factors that are linear or irreducible quadratics. Alright, so this is still the same function that we just worked with a second ago, so we don't need to find that list again, we already had it. So I'm going to put it here. This was my list of possible rational zeros for this particular function. So now what we have to do is basically move along this list and find one that works. So I would generally try to start with +1 and -1 and see if those values, when substituted in, give me a value of 0. So I'm using that remainder theorem from before, right? The way we can just directly substitute in the number and find the remainder. So it's just a trial and error situation at this point. So I like to keep my work organized and say, let's try x equals positive 1. So y of 1 is going to be 2 minus 5 minus 11 plus 20 plus 12. And then I want to see if this is going to give me 0. So the more mental math here we can do, sort of the better. So this is going to give me negative 3 minus 11. So that's going to be negative 14. Negative 14 plus 20 is going to give me a positive 6. Plus 12 is not going to give me 0. So I don't need to waste my time like actually finding the specific remainder. I just want to know, is the remainder 0? If not, move on, because we got to move down this list until we find one that works. So now I'm going to go ahead and try negative 1. And so let's see what happens. If I plug in a negative 1 into the first term, I'm still going to get a positive 2. Into the second term, a negative 1. Let's list that here. Is going to give me a positive 5. Here, if I plug in a negative 1, it'll square out. Times negative 11 is negative 11. Here we'll get negative 20. And then plus 12. So let's see, this time we're going to get 7 minus 11. That's negative 4. And then negative 4 minus 20 is negative 24 plus 12. That's not 0. Now, I do think it's worth it to try the remainder theorem, plugging in the number for 1 and negative 1, because it's relatively easy. We can almost just do it mentally and see if it works. But once you get past 1 and negative 1, especially with as many terms as are in this polynomial, I would start checking the zeros using the synthetic division way, because you're going to have to do that anyways if you want to completely factor the polynomial. So we want to just keep going down the line and trying, but we can choose whatever order to go when we want when testing these values. I would always test 1 and negative 1 first, but do I really want to test 1/2? I mean, it's not that bad, but I don't typically, want to deal with fractions if I don't have to. So we can go ahead and move on and try the next integer and try x equals 2. So it's just like a guess and check type of situation. So I'm going to go ahead and try x equals 2 using the synthetic division method. So let's see, 2, negative 5, negative 11, 20, and 12. Drop down the 2. 2 times 2 is 4. Add down, I get negative 1. I get negative 2. Add down, I get negative 13. Times 2 is negative 26. Add down, I get negative 6. 2 times negative 6 is negative 12. Negative 12 and 12 is 0. So that worked, right? That worked. I got a remainder out of 0. So what that means is that 2 is a 0. So we did the first part. Use the rational zeros theorem to find a real 0 of the polynomial. We made the big list. We went down the list, tested them until we found one that worked. Once you have one that works, now you can work on factoring it into linear irreducible quadratics. Okay, so what do we know? We know that now x equals 2 is a 0, which means x minus 2 is a factor. Right? X minus 2 is a factor. And then these numbers here become the coefficients of my quotient polynomial. So here's what we have so far. We have that y, that was the name of the function here, is currently factored to x minus 2. And then because it was a degree 4 polynomial, this 2 has to go in front of x cubed, a degree 1 less. So 2x cubed minus x squared minus 13x minus 6. So this is where I'm at so far, and now I have to keep going. Right now I have to factor this cubic polynomial. So when I have a cubic polynomial that has 4 terms, I can potentially try to factor by grouping, but for this particular problem, it doesn't work. So if I try factor by grouping, it doesn't work. It's worth a shot. I'm telling you it doesn't. So what do we have to do? we have to keep going with testing possible rational zeros. So here's the benefit. I don't need to do the whole P's and Q's thing again. I don't need to find the factors of 6 over the factors of 2, because this still comes from this original polynomial. So what I'm doing now is I'm working with this smaller polynomial, and I want to continue along the same list to determine another zero, right? I have to find another zero. So we shouldn't try 1 and -1 on this smaller polynomial. It's not going to work. If it didn't work for the original one, it's not going to work for the smaller one. So don't try. I'm going to kind of like write some notes here. So don't try x equals 1 or x equals -1. We could try x equals 2, because it's possible that there's another factor of x minus 2, right? When you factor something, you could have x minus 2 times x minus 2 times, x plus 3. There could be more than one copy of x minus 2. So don't try any that didn't work before. We could try x equals 2 again. So we could try x equals 2 again. I'm just letting you know it doesn't work, right? X equals 2 doesn't work. But we wouldn't know this unless we worked through it, but just to kind of save ourselves some of the work on this problem, we could try x equals 2, it doesn't work. What I am going to go ahead and do is try x equals -2. So when I say try x equals -2, it's on the smaller polynomial that's left over. So 2, -1, -13, and -6, right? So these values down here. And so I'm going to drop down the 2. -2 times 2 is -4. Add down, I get -5. -2 times -5 is 10. If I add down, I get -3. -2 times -3 is 6. And hey, this one worked. Of course, I knew it would, that's why I picked that one. But just to kind of show you where you should go from there in terms of your guessing and checking. So now these numbers, 2, -5, and 3, become the coefficients of a degree 2 polynomial. So we have -2 is a 0. So this is what we have from this work. We have -2 is a 0. So x plus 2 is a factor. So here's where we're at so far with our polynomial. Switch colors one more time. So our polynomial is x minus 2, x plus 2, and then 2x squared minus 5x minus 3. So these numbers go in front of a quadratic. And then once we have a quadratic, there's no need to ever do the synthetic division thing again, right? So we can either factor this thing. If it doesn't factor, then we can stop, because this problem just wants us to factor to linear irreducible quadratics. This does happen to factor. So we have x minus 2, x plus 2. This factors to 2x plus 1 times x minus 3. So I'm going to go ahead and box that in. That is my final factorization of the original degree 4 polynomial. Let's stop and look at basically a theorem, the maximum number of real zeros. A polynomial cannot have more real zeros than its degree. So if I have a degree 4 polynomial, then I can't have any more than 4 real zeros. It's possible to have less than that, but I can't have any more real zeros than the degree of the polynomial. In this last example, we want to solve this degree 6 polynomial for its real zeros. So the first thing I want us to observe about this polynomial is that there's an x in every single term. So the first thing that I'm going to go ahead and do is factor the x out of every term, and then I will automatically find myself at least one of the zeros. So I'm going to factor out the x, and I'm left with 3x to the 5th minus 19x to the 4th plus 18x cubed plus 86x squared minus 165x plus 45 is equal to 0. So I automatically know that 0 is one of my zeros. I could set x equal to 0. However, that's not going to be helpful in terms of using like a synthetic division. So what I have to do is look at the remaining degree 5 polynomial and find the list of possible rational zeros for this degree 5 polynomial. So I'm going to go ahead and start that list of possible rational zeros. So it's going to be the factors of 45, right, the last constant term over the leading coefficient 3. So the factors of 45 over the factors of 3. So the factors of 45 are going to be plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 9, plus or minus 15, and plus or minus 45. Those are all the factors of 45. And the factors of 3 are just 1 and 3. So we're going to go ahead and think about all these combinations. So 1 over 1 and 1 over 3. So we have plus or minus 1, plus or minus a third. We have 3 over 1 and 3 over 3, which is just 1. We have 5 over 1 and 5 over 3. So plus or minus 5, plus or minus 5 thirds. Then we have 9 over 1 and 9 over 3, which is just 3, and we already have that, so plus or minus 9. I have 15 over 1 and 15 over 3, which is 5, and we already have that, so just 15. And then 45 over 1 and 45 over 3 is 15, which we already have. So this right here is my list of possible rational zeros to choose from. All right, so now we can go ahead and move down this list and try to see if any of these are zeros to this polynomial. So remember the 3x to the 5th, the degree 5 polynomial. So we'll go ahead and start trying out some of these values. I can try x equals 1. That's going to be 3 minus 19 plus 18 plus 86 minus 165 plus 45. And remember that I don't have to actually find the specific value. I just have to decide whether or not this is 0. So one of the things I like to do is just look at all the positive numbers. So 3, 18, 86, and 45, and think about whether or not those are going to end up canceling out the negative values that are here. Sometimes it's more obvious than others. So we can think 3 and 18 is 21, and 86 is 107, and 45 is going to give me 152, which isn't going to cancel out negative 19 and negative 165. So this is not 0. And then we go ahead and try, well, how about negative 1? So remember that we're plugging it into this version right here. So if I plug in a negative 1, I'm going to end up getting negative 3, excuse me. If I plug in a negative 1 right here, I'm going to get minus 19. If I plug in negative 1 into negative 8, or into 18x cubed, I'll get negative 18. This will stay positive 86. This will become positive 165. And then 45 stays positive. There's no x's there, right? So remember to plug it into this one here, not the original one, because that's going to affect the signs, right? And so let's see, there's a whole lot of positives that's not even going to come close to canceling out the negatives. So we can see 86, 165, 45 are all positives, and they're not going to cancel out these small negative numbers. So this is also not 0. So then we're going to go ahead and try x equals 2. At least I'm going to try, not x equals 2, x equals 3, because I don't personally want to test out 1/3. You can, but I just choose to move to the next integer value. So if I try x equals 3, I am going to try it with synthetic division. So we're going to take 3, negative 19, 18, 86, negative 165, and 45, and see what happens. So if I drop down the 3 times 3 is 9, I get negative 10 if I add down. 3 times negative 10 is negative 30. If I add down, I get negative 12. Here, 3 times negative 12 is negative 36, so I get 50 if I add down. 3 times 50 is 150. And then negative 165 plus 150 is negative 15. Negative 15 times 3 is negative 45. So adding down, I get my remainder of 0. So we know that 3 is one of the zeros of this polynomial. So I'm going to go ahead and move this up a little bit to make myself some space. So in terms of my list of zeros so far, I don't want to forget I have 0 because of this initial x that I pulled out. Now I have 3 on the list. But I have to keep going, right? So the maximum number of zeros I can have is 6 because I had a degree 6 polynomial. So I have to keep working through this, and these coefficients would be on a degree 5 polynomial. So I would have to just keep working. Now, one of the things we can do is instead of continuing to redraw a synthetic division separate from this one, what I can do is just sort of do another synthetic division little bracket right here, and then test out another value. So remember, there's no point in testing out 1 and negative 1. If it didn't work for the original, it's not going to work for the smaller parts, right? It's not going to be a 0 of the smaller factors. We can try any that have already worked because we could have a repeated 0. So if I want to, I can try 3 again. So if I try x equals 3, so let's see, we'll bring down the 3. And we'll get 3 times 3 is 9. Negative 10 plus 9 is negative 1. 3 times negative 1 is negative 3. If I add down, get negative 15. 3 times negative 15 is negative 45. If I add down, I get 5. And 3 times 5 is 15. Negative 15 and 15 is 0. So I do get out 0 as the remainder. So 3 is a 0 of what we call multiplicity 2, because that factor is appearing twice for the original polynomial. So if we wanted to factor this completely, in other words, so far we have x, and we have x minus 3, and we have another x minus 3, and then there'd be, of course, some other polynomial here, more polynomials as we continue on. But we have a repeated linear factor. All right, so now we could theoretically test 3 again, but what we've gotten to at this point is this is a degree 3 polynomial. So this was degree 5, this was degree 4, so this one's going to be a degree 3. So what I'm going to do is take these values, make them the coefficients of a degree 3 polynomial, 3x cubed minus x squared minus 15x plus 5. And I want to think about setting this equal to 0. Well, this is 4 terms on a degree 3 polynomial, so I can try factor by grouping. Now, it won't always work, but on this one it does, which is really nice. So I can factor out an x squared. I have left 3x minus 1. I can factor out negative 5, and I have 3x minus 1. So I get x squared minus 5 times 3x minus 1 is equal to 0. So to find the remaining zeros, I can set each of these factors equal to 0. Well, x squared minus 5, I get x squared equals 5, or x equals plus or minus rad 5. And then here I get x equals positive 1/3 if I add the 1 and divide by 3. So these are the rest of my zeros. So I had 0, 3, I have 1/3, and I have plus or minus the square root of 5 as the rest of my zeros. And then I can, not that the problem asked me to, but I can write the completely factored version now. We have x minus 3, x minus 3, which is x minus 3 squared. So I'm going to write it like that. And then we have x squared minus 5 and 3x minus 1. So that's this polynomial completely factored out into linear and irreducible quadratics. So here are my zeros. What we should notice is that we have a total of 5 of them, 1, 2, 3, and then plus or minus 5 is 2 more, which is 1 less, right, than the total degree of the polynomial. So we can have at most 6, and we had 5. Another thing that I want us to notice about the list of zeros is that 3 and 1/3 were the rational zeros of this degree 5 polynomial, and they were on this list. So 3 was on this list, and so was 1/3. So I elected to skip 1/3, and I ended up finding 3 was one of the rational zeros. But if I would have done 1/3, I could have found a 0, just as fast. So all the rational zeros will be on this list, but radical 5, that's an irrational number. So it was not on this list. So the reason why I bring that up is because sometimes what students do is they kind of like try to work the system, and they're like, oh, find all the zeros. Okay, they all have to be from this list. So what I'll do is I'll just check them all. So I'll just go down and I'll check every single one of these numbers, plus or minus versions of them, positive and negative, plug them in or use synthetic division, and then find all of the zeros. So that would work if they were all rational zeros, but you would never find them all using that method on this problem because radical 5 isn't rational. So we have to be able to do this process to find all of the rational and irrational zeros for a given polynomial. So here are my zeros, and sometimes you will see 3 written with a m2 next to it or multiplicity 2 next to it because of how the factor is repeated.